Okay, so let's continue with question 1. It says, follow the steps to compute the trigonometric Fourier series S1 of t given below in figure 1, and we're going to go through these couple of questions. So first of all, take a good look at the signal. We've got a periodic sequence basically coming through here, and we want to answer what is the period of S1 of t and what is the fundamental frequency F0. Okay, so the period is the duration by which the signal will repeat itself, and basically if I was to set my reference at t equals 0, notice that it repeats itself after 0.5 seconds. So here the period is 0.5. Okay, so let's write that down. Period 0.5. Okay, so correspondingly, to calculate the fundamental frequency, it's the reciprocal of the period. Gives us 2 Hz. Fundamental frequency of 2 Hz. Okay, so let's come back to the question. Part B asks us to find the DC component of signal and find also A0. Well, having a look at this, there is, just graphically speaking, okay, there is no offset. Okay, if you was just to eyeball this, you'll notice that if I was to integrate this particular area, it will cancel with that one, and integrating this area cancels with that one. So we expect there to be no DC component, and we'll show that mathematically by working out what A0 is. Okay, so let's do that next. A0, I've written up here, definition. Take some time. Okay, just to calculate this particular expression. Now, our S of t might look tricky because it's not a continuous function, it's piecewise. So I'll just do a quick sketch over here. Okay, and it ends at 0.5. This is a discontinuous and piecewise function, so we will have to break this up into 3 different parts and integrate them separately. Okay, so the amplitude was 1 and -1 respectively, and let's go back to the diagram and find out where this point is. Okay, so over here I'm looking at that point there. It's basically halfway between 0 and 0.25, so that value is going to be 0.125. And similarly, that point there, I can come over to the diagram and work out what this is. So I'm after that x coordinate over there, so it's halfway between 0.25 and 0.5. Okay, so the value for this should be 0.375. Alright, so evaluating our A0, we basically put in everything we know. So the period, again, that was 0.5. Integral between 0 to t. Now, I'm not going to write t here because I know this is a piecewise function. So I'm going to write it a section at a time. So this integral begins from 0 and goes up to 0.125. And the value of this function is equal to 1. Okay, so that is the first region of our integral. That takes care of this bit here. Next, let's keep going. We want to integrate over this region now. Okay, I'll shade it in red. So what should the lower limit be? It should be 0.125, and the upper limit would be 0.375. And the amplitude of this is -1 dt. Okay, and finally we have this region shaded in green, okay, to account for. And to do that, it's the same thing. We integrate over, this time the lower limit is 0.375, upper limit being 0.5, amplitude of this being 1 dt. Okay, you could do that, and basically all we want to do is integrate over the period, which is fine. Okay, so let's keep going. A naught equal to 2 times, oh actually I should clarify here, this coefficient 1 on t really does apply to the whole thing, so it's perhaps more correct to put in the parentheses, which I'll do here as well. Okay, so continuing on with our integral, 0 to 0.125, the negative here I'm just going to put out the front, so t 0.125, 0.375 plus t 0.375, 0.5, okay, close brackets, and then of course we go upper limit minus the lower limit, leave the 2 out the front, upper limit minus the lower limit, this is 0, I won't write it in, minus 0.375 upper limit minus the lower limit plus upper limit minus the lower limit. Okay, and if you were to compute this in your calculator, it will actually give you 2 times 0. Okay, so this whole thing will give you 0. Alright, now I'd just like to show you something a little bit interesting. Notice that in my definition I've written it as 0 for t. Okay, whereas in the PDF you will notice that I typeset this as t0 plus t. Now it's really immaterial where you begin the integral. Okay, as long as you take the integral over one period, it doesn't matter, it gives you the same answer. So today I could have alternatively done the same question by assuming the period beginning at negative 0.125. I could have done that. I could have started at this point over here, okay, and ended at this point over here. I could have done that, and in fact I'll get the same answer. Okay, and perhaps this second approach that I took is probably going to be easier, because that means I only have 2 regions of integration rather than 3. Okay, so I'm going to demonstrate this procedure basically for AN and BN. Okay, but that was part B here, the calculation of A0. You can compute that integral over one period. It doesn't matter where you start, as long as it's over one period. Okay, so let's go on to question C. Oh, actually, let me put that down in writing just to make sure you understand. So I could have alternatively computed A0, which is 1 on t. Instead of having the limits between 0 to 0.5, I could have alternatively gone with the limits of negative 0.125, okay, which is that x coordinate there, and I could have integrated over there and ended here. That would have given me the same answer. Okay, so I could have gone that to 0.375 s of t dt. I could have done that as well, and it will also give you 0. Okay, so let's continue. We have here is s1 of t an even function. Okay, well, even means is it symmetrical about the y-axis? Okay, in this case it is, because whatever's on the right hand side, if you mirror image that, you'll get it on the left hand side. So mathematically speaking, I can say s of t is even because s of t is equal to s of negative t. This is like a mirror image about the y-axis. Okay, so that's part B. Let's have a look at part C. Although it's part C, actually, let's have a look at part D. Part D asks us to find the AN and BN trigonometric Fourier series coefficients. So let's go ahead with working that out. So AN, defined as 2 on t, integral between t0 to t0 plus t, s of t cos 2 pi n f0 to t dt. Okay, So again, I can start my integral wherever I like, but because the integral will probably simplify if I choose a starting point at negative. So just a quick sketch. Okay, it'll probably be easier if I integrate starting from negative 0.125 all the way up to this point here, 0.375. It'll probably be easier if I consider this period instead. Okay, so that's what I'm going to do with AN, and we'll see how it turns out. So let's begin. AN is equal to 2 on t at 0.5. Integral, again, I'm going to break this up into two pieces, seeing this is a discontinuous function right here, and in particular that discontinuity there is 0.125. Okay, so the upper and the lower limits are going to be 0.125 here and 0.125 there, and the amplitude of that function is equal to 1, so that's my s of t, multiplied by cos 2 pi n f naught t dt. This is the first part of the integral on this side. Okay, then I need to come over here and compute the second portion. Okay, so this one here begins at 0.125, goes all the way up to 0.375, and this particular amplitude here is a negative, so it's probably better I just put a negative here. So that's your negative 1, and cos 2 pi n f naught t dt. So there are our two integrals that we need to deal with. Alright, so let's keep going. Oh, and once again, it's perhaps better if I include this in brackets, because that coefficient out the front will need to be multiplied by each of these integrals. Okay, so let's keep going. So that's 2 divided by half, we give 4, so I'll just evaluate that quickly. Now, integral of the cos, that gives you a sine. So I have here sine 2 pi n f naught t divided by the derivative of the inside. So in this case it will be 2 pi n f naught, okay, between the limits of negative 0.125 and 0.125. Okay, so that computes our first integral. We do the same thing over here. So leave the negative sign alone, integrate the cos, turns into a sine, and divide by derivative of the inside. Okay, close the brackets. Alright, now the rest is just algebra. Okay, so evaluating this particular definite integral, I'm going to start by factorizing everything by this denominator here, just to make life a little bit easier. Okay, and I'm going to substitute in the limits. So I'm going to plug in 0.125 into t, and what you find is this turns into sine pi n f naught, so multiply that, 0.125 times 2 gives you 0.25, so that's like a quarter. So I'm just going to go ahead and write that as sine of pi n f naught on 4. Okay, so that's your upper limit minus the lower limit. So again, I'm going to put that in for t, and that should give me now, instead of a positive 4, should be a negative 4. So that will give you sine, I'll just write that down a little bit further, sine pi n f naught, and that will give me a negative on 4. Okay, so that computes that one, and then of course minus, then we substitute in the upper limit. Okay, so if I go 0.375 multiplied by 2, that gives me 0.75, so that's like 3/4. So I'm going to write this as sine of 3 pi n f naught on 4. Okay, so that's your upper limit minus the lower limit, and we already saw this before, that turns into a quarter. So I'll go sine pi n f naught on 4, like this. Okay, so it may look bad, but let's work through this one at a time. Okay, it will simplify and work out. So don't let this intimidate you in any way. Let's keep going. Okay, so we know that okay, in simplifying, let's just start from the very start. We have here 2 on pi n f naught. The 2's will cancel from numerator and denominator, so that's what we'll get as a coefficient. Okay, now after this, so sine pi n f naught on 4. I can't do much with that, I'm going to leave it. But here, we know that sine is an odd function, so we can remove this negative sign from its argument and instead write this expression as a positive sign. Okay, that will help us simplify, and look, this is pretty good because now we've got 2 like terms. We can combine these. Let's keep going. So this becomes expanding this bracket, so negative sign. Okay, we can't do much with this either, but at least we can expand the brackets. That's what we get. And now here, negative gives you a positive. Sine pi n f naught on 4. Okay, and good, we've got another one. Okay, we've got another one of these sine terms here we can combine out here. So finally we have here, looks like we've got 2 on pi n f naught, so that's going to be 3 lots of sine pi n f naught on 4. Okay, so that's combining this term, and this term. So I've got 3 of them, minus sine 3 pi n f naught on 4. So it simplifies quite readily. Okay, and we can actually go a little bit further because we actually know what the value of f naught is supposed to be. Okay, we worked that out earlier in the question. F naught was equal to 1 on t, which we agreed was equal to 2. So we can substitute that value in and further evaluate this. Okay, giving us, so 2 on 2 will give you 1. Right? Numerator cancels down even further. So here we have 3 sine, and again, if we put that in there, we have pi n on 2. Alright, good. Have here minus sine, and this also will cancel down to getting 3 pi n on 2. Okay, that's good. So this basically gets our expression for an. Alright, very good. Now let's keep going with bn. So keep this expression somewhere. We're going to come back to that in a moment. I'm going to start a new page and go ahead and write my expression, my definition for bn. So here we've got bn is equal to 2 on t, integral between t0 to t0 plus period s of t. Now this is your sine basis functions, so we're multiplying this with your sine 2 pi n f naught t, and of course dt. Okay, now before we even start, let's have a good look at what we answered just before. Okay, part C says, is s1 of t an even function? And we said in that particular question, in this particular question, we said it was. Okay, now let's just reflect on what the meaning of b of n actually is. B of n gives us the odd components of the function. Now, if our s1 of t, if this is our signal and it was entirely even, it means we expect there to be no odd components. Okay, if there is no odd components, so remember I made an annotation here, the sine basis functions were the odd components of the function. Now, if our signal is purely even, we expect there to be no odd components, which implies that your bn coefficients will go to 0. They will work out to equal 0. Okay, so it's good practice just to verify this, so I'm going to do this in tutorial. But it's a property that you can use to your advantage if you were asked to work out the Fourier series in the future. Okay, So let's do that and actually go ahead with the computation of Bn, and we'll show you that it indeed goes to 0. So let's have a look. Let's come back here. Alright, so again we follow the same procedure. This is a piecewise function. Okay, remember our function. And again I'm going to take the integral over negative 0.125 to 0.375. And the reason for that, once again, it simplifies our integral into 2 parts rather than 3 parts. Okay, so let's begin. Bn is equal to 2 on t. T we agreed that was 0.5. So our integral, I'm going to break this once again into 2 parts. Negative 0.125, and it goes up to that point there, which is 0.125. 0.125. Amplitude being 1. 2 pi n f naught t dt. Okay, so that's the first region. That takes care of that bit. Now I'm going to go and take care of this bit. Okay, so let's move this aside. Keep going. Okay, so that's going to be I'll put the minus because this is an amplitude of negative 1. Integral between 0.125 to 0.375. Okay, so that's the negative 1 accounted for. Sine 2 pi n f naught t dt. Okay, and again, that coefficient really should envelop the whole thing. Oh, it didn't work. Okay, so I'll put the brackets around that. Okay, very good. Alright, so let's keep going with the evaluation of this definite integral. So 2 divided by half, 4. Okay, evaluating this integral, a sine goes to what? A negative cos. So negative cos 2 pi n f naught t, and remember we have to divide by the derivative on the inside, so same thing. Okay, and don't forget your upper and lower limits. There it is. Okay, and then we have a minus here. Preserve the sign, integral with a sign. Again, that goes to a negative cos. Okay, divided by the derivative on the inside. And once again, don't forget your limits. Close brackets. Okay, and of course, after this is just algebra. I'm going to factorize like I did in the previous question. So 2 divided by 2 gives you 4 divided by 2 gives you 2. We have here 2 on pi n f naught. Okay, and then now I see this negative sign here. I can probably rewrite this and flip the limits of this integral just to make my life a little bit easier. So I'm going to rewrite this with a flipped limit, just to clean things up a little bit, so a little bit easier to handle. Plus, minus. Again, I'm going to flip the limits and factorize out the negative. Okay, so it's going to be negative 0.124. Like that, 0.375. 0.125. So I'm flipping the limits, I'm getting rid of this negative sign. Okay, so still we go upper limit minus a lower limit. Okay, so upper limit, I substitute this in. I get here cos negative 0.125 times 2 gives us negative 0.25, so that's like negative a quarter. I'm going to put the negative up here. F naught on 4, okay, divided by 4 is a quarter. Okay, so that was our upper limit minus the lower limit. This is it. So that's cos, once again, substituting this inside gives us pi n f naught on 4. Okay, 2 times that gives you 0.25, okay, which gives me the 1 on 4 here. So that computes that definite integral. Now let's have a look at this one here. So minus, plugging in the cosine plugging in the value into the cosine. So I have here pi n f0 on 4. Okay, and then minus, upper limit minus a lower limit, cos, and putting that in there gives me 3 pi n f0 on 4. Okay, so once again it might look bad, but let's work with it and it will simplify. And it actually works out to a surprisingly nice answer of 0. Okay, so let's continue. 2 on pi n f0. Okay, so cos is an even function. Yeah, so if it's an even function, I can take this negative out the front and I don't have to change the sign. So that remains as cos on 4. Okay, and look, we have another one of these. So this will actually cancel with that one. These two terms will cancel. Okay, let's keep going. Cos pi n f0 on 4. I have to do something about this one, but that's okay, we'll leave it. Plus cos 3 pi n f0 on 4. Reason why this is positive is negative, negative, positive. Okay, so let's continue to simplify. We have 2 on pi n f0. These disappear, we agreed on that. I'm going to write cos 3 pi n f0 on 4 first, and then I'm going to write minus cos pi n f0 on 4. Okay, so it might look pretty ugly still, but let's keep putting in the numbers. So we saw that f0 is equal to 1 on t, it's equal to 2. So let's put that in also. Yeah, pi n, and this is where it becomes very nice. So we have 3 pi n on 2 minus cos of pi n on 2. Okay, and let's have a look at what this really means. Okay, so we can simplify this further actually. N, we agreed on, has to be integer because they're related harmonics. So n is always an integer number. Now let's have a look at what a cosine looks like. Okay, let's come back to the basics. We have a cosine function right here. Now, if I just consider this over one period, what are these values here and here? Are they pi on 2 and 3 pi on 2? Right? So if I was to extend this infinitely for n period, basically the effect is you're choosing every integer multiple of 3 pi on 2 and every integer multiple of pi on 2. So really, it doesn't matter what n you choose as long as it's integer, you're always going to get a cosine of angle that is equal to 0. So in essence, this whole integral works out to 0. And that is to be expected because we said our original signal, right, this was an even function. So of course when we try and find out the odd basis functions with the sine components, it doesn't exist. So therefore all of the coefficients will turn out to be 0. So it makes sense. Okay, so now let's use the f-series.p function to plot and check my results. Alright, so I coded this f-series function for you just to help you check your results. It takes in 4 arguments. It takes in the a0 that you calculated, which should be a single value, and it also would like to take the first n coefficients of an and bn. Okay, you actually have to feed it a vector of numbers. We'll see that in the code in a little bit. Okay, and the code also expects that an and bn are of the same length. Now, f0, that simply just reflects your fundamental frequency. That's for plotting purposes. This function will output 2 parameters, f and t. F is basically your Fourier series plot. We'll see the in a moment. And t is the time vector, the time base. Okay, so let me boot up my program. I've coded this in advance, so let's just have a look. Okay, So I've got here capital N represents the total number of coefficients that I'm going to compute. So in this case, I've chosen a very large number of 120 coefficients. So if in evaluating AN and BN, I'm going to get 120 values. Okay, so that's basically the first 5 lines of code right here. And of course I declare F0 that was equal to 2. We saw that from the question. So I'm just going to run this piece of code and let's have a look at length of AN. So as I said, it's 120 coefficients. Length of BN, okay, is also 120 coefficients. Now the program will only work if AN and BN are of the same length. Okay, and here I basically just coded the functions in, but you will notice if you were to actually pick some values from this BN vector, it will all be 0. Okay. Alright, let's go ahead with this. Okay, so that's basically the Fourier series with 120 coefficients. So it looks pretty good. And I'll continue over here, plot the red over the top. So the red line is basically our original function over one period. Okay, so this is, notice that I've got here between 0 to 0.5. Okay, so this is one period between 0 to 0.5, and the blue line is your Fourier series representation. Now the more coefficients you use, the closer you will get. So for example today, if I didn't choose 120, let's choose some very low number. Let's say for instance we're just using 5 coefficients and we ran this code again. So notice your approximation is not going to be very good. I mean, it does its job, it looks roughly the same, but it won't do as good of a job as 120 coefficients. So the more coefficients you use, the closer you will get. So for example, let's try 20. Let's run that. Okay, so it gets closer. And of course, if you use 100, it'll get closer still. And you might ask, why did I choose 120? Well, it's just some arbitrary large number that I came up with. Okay, so see you in question 2.